There's no denying the recent advancements in computer vision. We went from edge detection to facial recognition to real-time object classification in under 2 decades. Self-driving cars may be next on the agenda, and if there's any hopes of man remaining superior to machines, it's probably not going to be in any visual recognition task. Which begs the question, do machines see in the same way that we do? This is Data Skeptic Consensus, and the 19th installment in our series about how multi-agent systems achieve collective decision-making. Today on the show, I speak with Adrián and Martín about the paper Convolutional Neural Networks Deceived by Visual Illusions.
Hi, I'm Adrián Martín. I'm a postdoctoral researcher at Universitat Pompeu Fabra in Barcelona, Spain.
Welcome to the show. Tell us a little bit about what you study there.
Well, as I said, I studied some years ago, so now I'm doing my second postdoc already. What I studied was mathematics and computer science, which then led me to a computer science master's and then a PhD on image processing. And now we work basically in image processing and computer vision techniques with some inspiration from models that comes from the study of vision in humans.
Gotcha. So I know we always hear this analogy that deep neural networks are kind of like the layers of the brain. And I think sometimes neurologists cringe a little bit when we make the comparison, but I'm not sure how much they should cringe. Maybe some of it's fair. What's your perception there on the comparison between a neural network and an artificial neural network and a human neural network?
I will definitely cringe also, like neurologists. No, it's artificial neural networks, of course, inspired on real neural network, but we all know that it's simplification. And actually, I think more and more people are working on trying to go from that simplification to some models that actually are more accurate.
And you'd mentioned part of your work includes looking at models that are, I don't know if you use the word inspired, but something along those lines from the human visual system. What are some of the ways in which one might be inspired in that fashion?
Well, actually, it's interesting because the model of artificial neural network is inspired on human vision. So when the people started to look at how they actually see, they start to model this vision as a stack of layers where we have some convolutions with some filters. Usually, when we do it in vision, we use oriented filters that can see horizontal, vertical, different frequencies. And so visions are actually like a very simplified neural network, I would say.
I'm not really someone who knows a lot about the brain, but I'm vaguely aware that our eyes are somewhat imperfect and the brain does a lot of cleaning up. Yet, I don't know if that's true in more computer vision. I think our cameras are maybe more accurate than the human eye in some cases, and there's not quite as much cleanup. Are these fundamentally different approaches, or at the end of the day, do both systems have basically the same data set?
No, I think it's a good analogy because, there is a part that is only the information that we receive from the exterior, let's say the luminance of the scene and the colors. This is some part, but of course we don't just see that. We process the information, and this is why we say that we perceive information, because there are some other things that are happening in our brain that are actually taking this information and combining it with everything that we know from the beginning, memories and all that stuff. So we actually, when we see a camera, when a camera is recording, it's actually taking just some information. So the analogy would be computer vision actually tried to do this analogy. So when you put some algorithms behind those cameras and you try to do something with that information, either retrieve some information, either like following someone, then you are more or less doing this analogy with how we see. Because when we see, we are doing something with that information. It's not only just perceiving the light, which is what a camera does.
So it's perceiving and processing then, is that right?
Yeah, exactly.
Yeah, makes sense. Well, the main work I invited you on to talk about was the paper titled Convolutional Neural Networks Can Be Deceived by Visual Illusions. I thought maybe we should start with a definition of a visual illusion. In my mind, I'm picturing like the image where it's either a candle or two faces or maybe some MC Escher art. Is there a formal, like mathematically satisfying definition of what a visual illusion is?
I don't think so. I think it's something that you see one, but it's not so easy to describe. I would say that visual illusion is something quite general. It would be some image stimulus, usually it's an image, that actually causes some illusion in your brain. An illusion, what we mean with an illusion is that what you perceive is not consistent with reality. So we can measure light, actually, with photometers, for instance, and we can measure a color that is different from the one that we are perceiving. So that's a visual illusion, when actually the reality and perception are not in the same phase.
Do machine learning or computer vision algorithms, at least the ones that people have created so far, do they end up having visual illusions the way people do?
Well, this is actually what we're trying to check in this work. Short answer, sometimes. There are sometimes and some type of illusions that actually are an illusion for us, and we can also see that they are an illusion also for convolutional neural networks.
And I would imagine you're probably familiar with the work on the fooling images, where you can use generative adversarial networks to trick some of these algorithms. Do you consider that a visual illusion, or is that something separate?
No, I would say that's different, at least from the type of visual illusions that we are targeting here. We're actually trying to go through the simplest visual illusions, because it's actually, I don't know, if you do some research about visual illusions, you will see that there are really many types and many categories, and it's really difficult to actually get some sense or some categories, some way of categorizing them. So we go to only a very simple ones, like these illusions that are usually called like brightness illusions or color illusion. So imagine it's something much more simpler than that. So imagine that we have an image that is separated in two sides. One of the sides is white and the other side is black, pure white will help us here. And then I put a small square in both of the sides. This square has a gray value, a gray that is between the black and the white. What is going to happen for all the observers is that the square that is over the black background is going to look lighter for us than the other square that is over a white background. This will happen always. And of course, we know that they have the same gray value because you can do actually this test with, PowerPoint and create this test for yourself. You are going to copy paste the same square and you are going to see that once that you put that one that you place one over the white and the other one over the black, they don't look the same for your eyes. And this is really something that is surprising when we see it actually in such a simple example. So those are the types of illusions that we are actually targeting here.
You've done a wonderful job describing a visual illusion on an audio-only podcast here, so thank you for that.
Thank you, I did my best.
When I think about that, though, and the way a computer sees, and I should probably put, quotation marks around the word seeing for the computer vision, but it sees it as some RGB pixel value. So surely the machine is not fooled by such an illusion. Is that the case?
That was the thing that we started thinking, right? Actually, we can imagine why, but there are many theories on why visual illusions happens to us. It's not clear at all. The theory that is more accepted is that there is something evolutionary on that. Our vision has evolution to see in a 3D world, and actually when we get some inputs that are 2D, that are very artificial, they somehow trick the brain because we are not used to that, and our brain and our perception is really optimized to see well in reality. But of course, a machine is not us, is not. But in what is similar to us is that most of the CNNs, when they are trained for an imaging task, they are trained in natural images. So somehow we are replicating the same process that happened to us, because when we are optimizing these machines, these CNNs or artificial neural networks, the same thing could be happening. And that's actually what we try to see.
When I learned the word pareidolia, which is, the tendency for the human eye to see shapes and regularity that isn't there, like seeing a tiger in, just what ends up being blowing leaves, at a very high level that appealed to me from some evolutionary perspective, that the human being who thought a tiger was there and ran probably lived to reproduce in a way that the person who wasn't scared and stayed and got eaten does. I don't know how scientific that is, but it sounds pretty good to my ears. Yet, aside from avoiding the wumpus mouse or things like that in a digital world, most computer vision algorithms don't have the same selective pressure. Do you have any hypothesis as to why they should develop these same sorts of tendencies?
As I said, the type of illusion that we are actually characterizing are much more simpler than that. So the hypothesis here is that, well, we train these neural networks to perform like very simple tasks because we actually wanted to see the problem as separated from other environments as possible. So say, for instance, we train a network to just do denoising, which is probably the most basic image processing task. Well, I don't know if image denoising is well known, but basically is if I have an image that has some noise, some perturbations that can happen because I'm taking the picture when the light conditions are not good, and we try to remove that noise, so those alterations. That's usually the basis of image processing algorithms. So first I do a denoising. So when you train a CNN for doing a denoising, what is happening there, a CNN is in the end is a stack of a lot of linear filters that are being trained in this process. And in these linear filters, what we start seeing are what some people call like basic linear filters, which are the ones that are descriptor of images, like the most basic. If you wanted to create an image in a very basic way, you will use first something that has vertical stripes, then something that has horizontal stripes. So these are the most basic components of an image. So if you wanted to decompose an image, basically. And the CNNs, when they are trained for something like very simple, like a denoising, when you check what are these weights, how are these filters that they have learned, you can see this type of filters. And now I get to the point. The hypothesis is that we actually have this same type of filters somehow encoded in our brain. So our neurons are, and this is again it's a hypothesis, but it's somehow proof in some neurophysiological experiments. We actually have this type of filters encoded in the big one, in the part of the brain that is actually in the retina. So that's the hypothesis, that actually the CNNs are, when they are trained, they are basically learning some structure that we also have in our brain in some simplified way. Okay, it's not for sure, it's not as complex as our brain, but somehow they're getting there.
Yeah, it's interesting. When I started reading the paper, I assumed that any ability that a CNN developed to notice a visual illusion would be something akin to a bug, right? If my eyes see different than reality, then my accuracy is not where I'd like it to be. But having concluded it, I'm walking away wondering if I should apply the famous phrase, it's not a bug, it's a feature. What are your thoughts on that?
That's actually our hope. What we see here is that there are some neural networks that are actually closer to our perception in some ways. So what we see in this study is that some of the networks that we test are actually reproducing in somehow these visual illusions in a closer way than others. So then the natural thing to think about that is that, okay, can we use that to actually build neural networks that are better in some way? Because if we think only about performance, probably this is not the case, because we know that we make errors, and our ideal goal would be that the neural networks don't make the same errors that we do. But there are some things in where human perception works much better than neural networks, and this is the case of adversarial samples. I don't know how much aware are you on this, but these adversarial samples are something that are inputs that we can put into the networks and make them basically collapse or fail in some ways that are really ridiculous, I would say, compared to humans. So say, for instance, these neural networks that are really, really good in recognizing classes in images. So say that we have these big databases of many types of animals, and there are these neural networks that are able to get accuracies which are actually better than human in recognizing, okay, this animal is a tiger, this animal is a lion. But then there are these adversarial samples in where you actually perturb just a bit the images. You put a little bit of noise, something that is actually ridiculous for us. Sometimes it's even difficult for humans to see what has changed between the original image and the new one. And then the neural network says that it was before a tiger, with a very big probability of being a tiger, is now, I don't know, a bird. So in that way, perception is still, thanks to God, I would say, is still better than machines on that. And our hope in in this work was to see, okay, maybe we have found a way to see if a network is closer to perception. So maybe there is a way that we can actually build neural networks that maybe they are not the best at performance, but they get better at perception, and then they behave better against this type of adversarial samples, for instance.
Yeah, the adversarial attacks, while fascinating, are also somewhat disappointing, that this algorithm that looks pretty good could make mistakes that are really blunders, right? It's not like a child who says a ukulele is a guitar and you understand the mistake. They're more worrisome errors. I don't want to over-exaggerate the connection, but do you think that some of the work you've been embarking on here might be the key around that if machine visual systems were better able to replicate some of these same base level phenomenon, could it be that inoculates them a bit from the adversarial attacks?
Well, that's for sure our hope. I wouldn't go that far. I mean, our best hope here is to actually have a tool to better understand these neural networks. And somehow this could get us closer to understand why they fail so significantly. And well, as I said, that would be for sure our best hope. And if we could do that, I think it would be really, really interesting. But I don't want to go that far.
Well, I appreciated your earlier description of, going into Paintbrush or PowerPoint or whatever and reproducing the gray box illusion. But tell me a little bit about your data set. Did you have a lot of abstract art projects, or do there exist common corpora for this kind of thing?
No, this is something also that it's a problem when you try to work with that, because actually visual illusion is a field that is mainly work in what is called the field of vision science, which is people who are actually trying to understand how this human vision works. And it's not such a big community. And I would say that most of the algorithms and most of the data sets that people have are small, reduced, and they are actually not prepared for something like machine learning that actually we need like big amounts of data. So this is actually a problem. And actually, when we were creating this work, we somehow felt like we had to invent many things. Like we had to create these illusions, based on, of course, collections of illusions, but we had to create the stimulus by ourselves. If we wanted to do like some replications, some other ways, we actually had to build from the scratch. So that was a problem, I would say. And I think we are closer to generate a bigger database, but there is no like a real gold standard right now for working on that.
Thanks to this week's sponsor, Nordvpn. Everyone needs to protect their home internet connection, and Nordvpn is one of the best choices out there with super fast servers in 59 countries. You can unlock Netflix and your favorite entertainment websites, protect your data at home and while traveling. There's absolutely no data logging, 24/7 customer support, 6 simultaneous connections supported, and with a 30-day money-back guarantee, how can you not want to give this a shot? Nordvpn is compatible with Windows, Mac OS, Linux, iOS, and Android. Basically everything. And that's with unlimited bandwidth. Nordvpn has an extension for the Chrome browser that is lightweight, user-friendly, and super secure. That makes this totally easy. And for Data Skeptic listeners, get 68% off NordVPN. That's only $3.71 per month, plus you get an additional month free by visiting nordvpn.com/dataskeptic and using coupon code DataSkeptic, all caps, all one word. nordvpn.com/dataskeptic. Well, in the effort to reproduce these illusions, or at least, I guess, see, and as you guys did find that indeed CNNs do reproduce the effects of visual illusions, could we zoom in on what that means? Do you do some sort of model introspection, or is it that you watch the trained model fail at a visual illusion task? How do you go about this empirically?
And the first experiment that we did, actually, there were many, but the first one was what we thought it was the simplest. There are some illusions, like the one that I described earlier, that happen for every human. So we don't need to actually test on human again. There are some that are already tested like many times in literature. So then what we did is actually, so this is an image and we have an artificial neural network that processes images. So I can input the same image and see what is the output coming from the neural network. Usually this type of visual illusions, like the one that I described it, they come in pairs. So what I would do with the same visual illusion that I told you before, I had one image in where the background is white and I have a gray square in the middle, and then I have this other image where the background is black and the square is the same square. Then I will input those images, these two images, on the neural network, and then I will compare the outputs. In the outputs, I will compare what has happened with the square. So then I can check if the square that is surrounded by black has a different intensity from the square that is surrounded by white after passing through the neural network. And this is what we actually found, is that when we say that we were replicating the same effect, is because if the square was lighter for us, this is what was happening after passing by the neural network, that the square has a gray intensity that it was higher than the square that was surrounded by white after passing through the neural network.
And where are you looking at exactly? Is that sort of the top level output layer, or are you inspecting some of the lower levels in that hierarchy?
That was also a question for us. Actually, we started working with neural networks that were used for classification, and there we had that problem because, as you know, you start with an image and then you go through all these layers and you basically lose the image and it transforms in something else, and then it's very difficult to actually see this. So what we did to, like, kind of a shortcut to that was to, okay, let's restrict ourselves first to neural networks that perform a task that is image-based. So for instance, image denoising. Image denoising is going to take one image and then output one image. So then we don't have that problem. We can directly go to the output of the neural network and compare there.
A lot of the techniques in the architecture of the CNN could maybe be destructive to this process. I'm thinking of pooling in particular, where, the kind of maximal value is taken. Are there any of these, I don't know if you'd call them regularization techniques, but sort of standard architectural features that would either obscure or enhance these effects?
Actually, what we found is that this paper is actually the detailed analysis, but the first work that we did, we actually published in the CVPR. In that paper, what we did was starting from a very basic architecture, actually very simple with 2 layers. We start playing with these type of things, like what happens if I put pooling, what happens if the pooling has this size or that side, or so we tried to actually cover almost everything, which was not such a good idea because it was very difficult to actually get an idea of what was happening. But what we got, and I think we got it from the analysis that is published in the paper, is that the most non-linear that is your system, for instance, pooling, if it's a maximum pooling, is going to make it really non-linear. The more non-linearities that you have in your system, the less evident that is the effect of the visual illusions. So actually, when we actually try this in very deep architectures, the effects that we observe are much, much smaller. So this somehow has the implication that in some ways, the deeper that we go, we can see that we are getting farther away from our perception, which is interesting, I think, because these are the type of networks that are actually having these big problems with something like adversarial attacks.
And I'm curious if you have any thoughts on whether or not these effects will, as you described, they're sort of fundamental. They're squares and edges. They're not necessarily the M.C. Escher art. Will the same effects scale up if you continue this work? Do you think you might see that these same networks have similar visual illusions from more complex structures like our human eyes do?
There were other works that more or less at the same time that we started working on this were finding this type of effects. So for instance, there is this network that these guys were creating a network that predicts the next frame in a video. It gets a series of frames and then at some point after be trained for that, it predicts the next frame. What they found is that if they get as a frame one motion illusion that is very famous that is called snakes, the snake's illusion is basically like kind of a snake is based on kind of rings and has some colors in blue, yellow. I think if the people who are listening can search snakes illusions, that would be the best because there's no way I'm going to explain it well. The funny thing of this illusion is that if you start looking at it, it starts moving around and you start seeing the snake moving as making some cycles. And what they found in this work is that this network that they were making to predict frames, the next frame in a video, it was able to predict actually the motion that we see. So which is something I would say more complex than the type of effects that we are seeing. After that, I think that there have been some other works that trying to see if there are some illusions that they're called completion, in where there are some type of shapes that the human brain, even if we see the image cut, for instance, if we see, the most typical is a triangle. You have a triangle where you have been cut in the corners, but your brain somehow is seeing the corners. So you are 100% sure that there are corners there, that even that they are cut in your brain, you can see those corners. So you have a very accurate idea that how those lines will go and get together as a corner. So they found also that in some networks that are complex, like for instance, for doing image classification, they could prove that actually this type of illusions could be seen.
What was the motivation to start looking into this? Why would you even begin to imagine that computer vision algorithm could be affected by the same visual illusions?
This was the original idea of Alexander Gomez, who is a PhD student in our group. And I would say that the motivation was he was bored. It was an original idea from his first month of the PhD, which I think is really impressive. And he basically arrived to Barcelona the 1st of August. I don't know if you've ever been to Spain, but if you come to Spain in August, it's a wonderful time for holidays, but it's a very bad time for working because most of the people are on holidays. Somehow the whole country stops that month. So he arrived there in Barcelona. It was his first month of PhD and basically was nobody around. He just got a lot of things to read. So he was going to work on the connections actually between vision science and neural networks. So there were some things there. And then he started looking at the models that vision science people were working with. And he noticed that actually this type of models, which are basically a stack of some type of convolutions and then some nonlinearity and then more convolutions, were basically like a very simple neural network. But actually in vision science, people don't train that. They tune the parameters until they get what they are looking for. So this was what originated his idea. And visual illusions are main thing that vision scientists have to actually play with these models. So let's say if they are building a vision model, the way that they can test if it's actually good or not, the visual illusions are the thing to test with. So then is, I think, when the years started working for him and said like, okay, maybe this is actually true with CNNs because they are really, really similar in the way that they are built. And they all are based on the same idea that the brain somehow can be described in a very simple manner as a combination of layers which are linear and non-linear. So all those things, and I guess being very bored in Spain in August were the main reasons why we started working on that. And then we arrived in September and he already had this idea and then we had to push it because it was, I think, really nice.
Well, bored in Spain sounds lovely if it produces insights like this one. I'm curious if you have any thoughts on where this line of inquiry will go over the next couple of years. Is this sort of a curiosity, or do you think this might be the tip of the iceberg in some fundamental insights into the nature of visual systems?
Well, we're going to continue trying to see this idea of using this to make some neural networks that are closer to perception can have actual future. This is the main output that we can try to find from that. And the other idea, and this is something that we are already working on it and having the first experiments and not being fully satisfied yet, is that until now what we have seen is, okay, if I have a stimulus that is a visual illusion for humans, in some cases it occurs that is actually a visual illusion for CNNs. But can we go the other way around? Can we find something that is a visual illusion for neural networks and then check if this is a visual illusion for us? What we thought it would be very interesting is that if we are able to do that, that would mean that maybe we can find a way to synthesize new visual illusions. And this would be really, really useful because, as I said, there is no a systematic way right now to actually get a database of visual illusions. And they are really interesting for studying how we perceive. So, and it would be for sure very interesting if we can use something that is completely artificial artificial to create an illusion that is an illusion for us as humans. So those are the two main paths that we see from here, because the first path, as I said, would be, okay, can we create neural networks that are closer to human perception? That's one thing. And the other is, okay, can we use the visual illusions that we get from neural networks to study how the human vision works? So the other way around.
Oh, that's very interesting. As a slight tangent, I'm not a juggler and I don't know too much about juggling, but from what I understand, at some point, mathematicians put some sort of systematic representation around juggling. And in a similar way, just because the algebra worked out ever so conveniently, they actually discovered new juggling moves by working the mathematics. Are you inclined to believe that a sort of more rigorous system could exist, first of all, for describing the set of all visual illusions? Maybe it's not so easy to encapsulate, but if so, might we have ways to do that and then make inferences from that language, if you will, of visual illusion?
That would be amazing. There was a study where there were some people who were trying to use all the visual illusions that are known right now. And they basically created a database and they put them all together. And then they use a neural network, one of these generative adversarial networks, to try to generate new illusions from that. But sadly, this study failed because visual illusions are so different between each other that the neural network was seeing a bunch of different images that it could not get any structure. So as you said, if we could get some mathematical description, something rigorous that can describe something that for sure will make an illusion, that will allow us to generate large collection of these type of illusions. And then from that, that we could try to actually use this type of synthesizers. It could be a GAN, a generative adversarial network. It would be any desynthesizing algorithms that try to produce new things from there. So for sure, that would be a wonderful thing. But I think we are quite far right now.
Yeah, I'm equal parts excited and other parts terrified that every ad I see on the internet will be a confusing, mind-bending thing capturing my attention.
Yes. That's another worry.
So I'm curious to wind up about what's next for you. Is this sort of the primary line of inquiry in your research, or are you working on broader questions as well?
I would say this is right now our preferred main line of study. But the other point that we are working also, as I mentioned before, these vision science models and the neural networks itself, they are based on this very simplified modeling where you just get a collection of linear, nonlinear operations and you go from that and try to replicate whatever task you're trying. And this is actually the basis of machine learning, this type of algorithm. And we're actually working on other models that try to be a bit more, use some kind of more complex models that try to replicate better what is actually happening in the brain or in the vision, which is a very good sharp for that. And then see if we can build from those models new type of neural networks that are somehow closer to how our brain works.
Well, it's very fascinating and has kind of been illuminating for me. I always thought of the human eye as maybe weaker than computer vision because we could engineer the computer version, but perhaps there's still a lot of important biological lessons to be learned here.
For sure, we know that there are many things in which machines can excel us and they are already beating us in some tasks, but there are still some things that luckily, that we can do that they can't do. So maybe we are, as you said, this could sound scary because we are trying to close the gap and take what is still only part of the human vision and try to put it on the machines. But I mean, it's a fascinating way to actually study how vision works because we actually don't know many things. That's for me the most interesting part. We use all these studies, and this included this thing with the visual illusions, to actually understand why we see, how we see, and how we interpret the things that we see.
Absolutely. Where can people follow you online?
I have a Twitter account, which is mostly in Spanish. So I think if you want to follow our work and a lot of nice things about visual illusions, I think the best that you can do is to follow Alex in Twitter, the PhD student that I was talking about. His Twitter account is Albiur, and I think he really likes this topic and he posts a lot of interesting things because Twitter is full of people who likes to play with visual illusion.
Very cool. I'm looking forward to following him as well. Well, Adrián, thank you so much for coming on the show to share this work and all of your research.
No, thank you very much for having us. It was a real pleasure.
That concludes this installment of Data Skeptic Consensus. Our guest today was Adrián Martín. Claudia Armbruster is our associate producer. Vanessa Burciaga does guest coordination. And I've been your host, Kyle Polich.